Let's get into a topic that is super critical for anyone working with malaria parasites. But man, does it cause a lot of confusion. Calculating hematocrit. So we're going to break it down with some real-world scenarios so you can walk right up to that culture hood and passage your cultures with total confidence. You know the feeling, right? You're standing there at the culture hood and these are the exact questions racing through your mind. You're just trying to keep your parasites happy, and all of a sudden you're hit with what feels like this high-stakes math problem. Get it right, your culture thrives. Get it wrong, and yeah, that's exactly what we're here to stop from happening. And that just hits the nail on the head, right? It feels like it should be easy, but the pressure is definitely on. But here's the good news. Once you really get the why behind all the numbers, the how just clicks. It becomes second nature. Okay, so first things first, we've got to build a solid foundation here. The biggest reason people get tripped up about this is because they confuse two related but totally different concepts: hematocrit and parasitemia. Getting this difference down cold, that's the key to, well, pretty much everything else we're going to talk about. Okay, so hematocrit, it's really all about density. It's simply the percentage of your flask's total volume that's made up of red blood cells. Now, parasitemia, on the other hand, tells you about the infection rate inside that red blood cell population. Think of it this way. If a hematocrit is all the houses in the neighborhood, parasitemia tells you how many of these houses actually have someone living inside. It's basically a measure of how packed your culture is with parasites. So right here, this lays out the key difference. See, when you're passaging a culture, you're juggling both of these things at the same time. You are diluting the occupied real estate, that's the parasitemia, while making sure the total real estate, the hematocrit, is just right for healthy growth. And you got to get them right. Okay, enough theory, let's get into the practice. Let's get our hands dirty and put this into practice. We're going to walk through 3 super common scenarios that, trust me, you will see at the bench. Starting with the one you do most often, your culture's been chugging along just fine, the parasitemia is getting a little high, and it's time to give those parasites some fresh medium and more room to grow. Pretty standard stuff. A tenfold dilution of the parasitemia, and we're shooting for a nice, healthy 5% hematocrit. So here's the deal. The trick is to break it down into 3 simple steps. Step 1, you figure out how much of your old culture you need to carry over to hit that target parasitemia. Step 2, and listen up because this is the one people always forget, you calculate how many fresh, uninfected red blood cells you need to add to reach your target hematocrit. And finally, step 3, you just top the whole thing up with medium. Easy. Okay, now for scenario 2, let's raise the stakes a bit. You're setting up a drug sensitivity assay, and here precision is everything. We often use a lower hematocrit like 2%, no room for error. Your calculations have got to be spot on, and here's where the thinking shifts a little, which is pretty interesting. Remember in scenario 1, we were adding fresh cells to get up to 5%. Well, here the amount of culture you need for your parasitemia might already put you over your 2% hematocrit target. So instead of adding cells, your job is actually to figure out exactly how much you need and toss the rest. And boom, here's the final setup. From a 10% parasitemia culture, we want to go down to 1% parasitemia with a final hematocrit of 2%. Let's tackle the calculations in 2 steps. Let's focus now on the 10% parasitemia culture to 1%. So here we're going to take 1 milliliter of the parasite from the old culture, and we got this by doing 1% parasitemia divide by 10% parasitemia, and then we multiply it by 10 milliliters, which is the final volume we want to be in. And so we get 1 milliliter. Now that the parasitemia is out of the way, we're going to focus on the hematocrit that we want. And we say that we want a final hematocrit of 2%. Let's adjust for the percentage that's going to come from the existing culture. We say we're taking 1 milliliter of the existing culture for the parasitemia. And so we say that this one gives us 0.1% of the hematocrit, because it's going to have red blood cells, though it's occupied by parasites, but it's still red blood cells. So we factor that in. So essentially we actually want to adjust by adding 1.9% more, because we already have 0.1% as a result of the parasitemia calculation, where we're taking 1 milliliter. So if we want it in a 10 milliliter flask, then it's 1.9% divided by the 100% red blood cells that we've made, multiplied by the 10 milliliters, and we get 0.19 milliliters of red blood cells that we have to take if we assume a 1 red blood cell suspension. Often it's stored more as a 50% red blood cell suspension, so you can adjust accordingly. So if we were to take the 0.19 milliliter, then we would add 9.81 milliliters of media. However, let's not forget the volume that would have been taken up by the infected red blood cells that we calculated for the 1% parasitemia, and remove that portion so that we end up adding 9.71 milliliters of our complete media. And now we will have our parasite at 1% parasitemia, and we're going to have 2% red blood cells or hematocrit. Oh man, we've all been there. The dreaded Friday afternoon disaster. You check your culture, the parasitemia is through the roof. The medium is turning yellow. The culture is totally stressed out. It's about to crash, and you have to do something like now. This isn't a routine passage. This is a full-on rescue mission. So the goal here is simple. We need to bring that parasitemia down, and fast, to take the stress off the culture. And you'll notice we're not going all the way up to 1%. We're aiming for 2%. Why? Well, it leaves a slightly bigger population of parasites to help kickstart the recovery in that fresh flask. So for this, we're also tweaking the hematocrit. We're going for 4%, just a little lower than the 5%. This gives them plenty of fresh cells to invade, but keeps the culture from getting too dense while it's recovering. It's all about giving that struggling culture the absolute best chance to bounce back. Okay, we've crunched the numbers. Now let's boil all this down into some real hard won wisdom straight from the bench. These are the pro tips and the common mistakes that can literally make or break your experiments. So this table is like your ultimate cheat sheet. Seriously, go ahead and screenshot this. It's perfect for your lab notebook. It lays out the standard numbers for the most common situations so you can stop guessing. So 5% for routine stuff, 2% for those precise assays, 4% for a rescue. Simple as that. And these are the little things that make a huge difference. Using fresh red blood cells, totally non-negotiable. Your parasites will thank you. Being consistent with your centrifuge settings. And please, 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 for the love of science, label everything right away. Future you will be so grateful. Now let's look at mistakes. Okay, let's talk about the number one mistake that I'm sure everyone makes when they're starting. You do the parasitemia math correctly. You transfer your infected culture, you add the medium, and you totally forget to add the fresh, uninfected red blood cells to get your hematocrit back up. And the fix? It's so simple. You just have to make it a habit. Just remember your total red blood cell volume is always made of two parts. The old cells you're carrying over and the fresh ones you're adding. Calculate them separately, add them together, and you will never ever have a sad low hematocrit culture again. Okay, let's zoom out for a second for the big picture. Why do we even care about this stuff? It's not just about keeping the parasites happy, it's about the integrity of your actual science. I mean, consistency is the bedrock of good reproducible results. And this quote right here, this is the big takeaway. Hematocrit can actually affect how fast parasites grow and even how they respond to drugs. So if your methods change from one experiment to the next, or if they're different from the paper you're trying to compare your results to, well, you're just comparing apples to oranges. Your data gets messy and your conclusions just aren't as strong. So that brings us to the end of this video. Thank you so much for checking out the video. I really appreciate you subscribing to our study group and giving the video a thumbs up. Do ask a question if anything was unclear, and I'm looking forward to catching you in the next video. God bless. Bye. Strong.